So I wanted to recap then about the required data structure for probability regression models in R. So to fit a binomial generalized linear model in R, you need the data organized in two columns bound together, one column of successes and one column of failures. Now the R command, as we saw in the last lecture, it needed to do this is cbind, and what this cbind does is literally just bind columns together. And once you do this, and you've got two columns bound together, one column of successes, one column of failures, you're then ready to fit generalized linear models to this data. So for our data example in R, what we've got here is a high, so this is a binding together of observations that have 1 if the respondent gave a high score and 0 otherwise. And what we've got here for Y low, we've got two columns. The first column will give a value of 1 if the respondent gave a low score and 0 otherwise, and then the second column will be 1 minus that. And then for Y medium, this is again a column of 1s if the respondent gave the medium score and 0 otherwise, and the second column of failures is 1 minus the first one. Okay, so it's slightly confusing that this data has to be set out in this format. So when we fit binomial generalized linear models in R, the basic set of commands works exactly as you've seen before. So you have two steps that R has to go through. Firstly, you've got to actually compute the model, call it something logical, and then you've got to explicitly ask R to summarize the results. Okay, and then what you have to do here, so we've saved the first generalized linear model. To summarize the results, you have to make sure that you get the name exactly right in the brackets. So the two high1.glms have to match. Similarly, the two high2.glm the generalized linear model, and then what you call up in the command summary. So you should see then that this is the same rhyme, rhythm, and reason as you've seen before in terms of the R commands and the set out of the two models. So this is a generalized linear high related to region. Family is binomial to tell R that you're fitting a probability regression model, and then you can specify a probit model if you want to fit a probit model. And the thing to watch for here, both similar models, so you'd expect similar models to give you similar answers and similar interpretation. So using a logit model then to calculate the probability that somebody gives a high score depending on the region. So what we've done here is we've extracted a bit of the R outputs here. We've got the table of T statistics, and again it's just the second row of this table downwards where the interesting action is, and we're looking for here p-values in the final column that are less than 0.05. So we've got here evidence of a possible difference for the London and Essex region. So we've got here a dot which indicates marginal statistical significance, and what we've actually got is a p-value in this sort of corridor of uncertainty. So the p-value is 0.0539, and this is in the corridor of uncertainty being 0.05 and 0.1. So strictly speaking, we've got no evidence p bigger than 0.05 for a regional effect, but probably the most nuanced way of expressing this would be to say there's weak evidence, p equals 0.0539, that those in the London region may be less likely to give a high score as the coefficient is both statistically significant and negative. Okay, it's slightly hard to interpret this because you're in this corridor of uncertainty. For the assessment, just say whether or not p is bigger than 0.05, but this would be the most nuanced interpretation of this. So I wanted to show you how to calculate the same probability that somebody gives a high score using the probit model. So the R commands given for this are on slide 3.5, and again picking out these T statistics, you get the following output from R, and the thing to watch for here is from the second row downwards. So Similar models should give you similar numerical estimates and similar interpretations, and you should see here that we get a very similar interpretation for the probit model compared to the logit model. Okay, so you've got weak statistical evidence of an effect. So for the assessment, whether it's an exam or coursework in your case, you could get by fine, just tell me whether or not P is less than 0.05. Probably the most nuanced way of interpreting this would be to say that there is weak evidence P equals 0.0538 of a regional effect, and the suggestion would be that those in the London region may be less likely to have a high score, as this coefficient is negative and borderline statistically significant. We're in this sort of corridor of uncertainty between P equals 0.05 and P equals 0.1, and this isn't necessarily something that would be important for your assessment for the module, because you just need to interpret at the 5% significance level, but it's possible to make a mess of the some numerical calculation examples again, and what we're looking for here is some sort of proof that similar models should give similar numbers. Again, this should give you some confidence that you're actually getting the thing right. Okay, so you're asked to calculate the probability that somebody from the London region gives a high score. So the way to do this is set the log of P over 1 minus P equals to the regression bit, and when I say log here, I mean ln natural log, irrespective of what is typed on the slide. So P over 1 minus P is the exponential of the regression bit, and you can rearrange to get that the probability here is 0.717 to 3 decimal places. Okay, so I just wanted to give you some extra practice and some extra detailed hand calculation examples. Now, it's something that is important when you're sitting a written exam for the module. It's still useful, I think, for just general education, just to have a handle and a feel for what the equations and what the numbers on the R output are actually doing. Okay, and then if you had to, how you might calculate these probabilities from first principles. So in this case, what you've got is a set of algebraic manipulations, essentially log of the probability of a 1 minus probability is a regression bit, and the same set of algebraic manipulations calculate the probabilities you've seen before. So I want to give a second example with the probit model then. So what you have in this case is that z to the minus p is equal to the regression bit, and then doing hand calculation examples for the probit model is just to keep the thing. This is limited resolution of statistics tables, and then what would happen at this point is that the probability of the z value of this number here, 0.58, which is 0.71904. So results then do give very similar numerical answers for both the logit and the probit model. Okay, so this is exactly what we were anticipating to find, that two similar models are giving us similar numerical estimates on a given data set. Okay, there are some slight differences in this case, but this is really to do with the limited resolution of the statistics table. So if you had more accurate statistics tables, you get a closer match between these two estimated probabilities here for the logit model and the probit model. Actually, I think an interesting exercise would be if you calculated these probabilities using R, you'd probably get a closer match than if you use the statistics tables to calculate the probit probability. To calculate the probability that somebody gives a low score on this survey. So it's the same basic set of R commands that you've seen before, and again the way this works, this sort of two-step process, R will do exactly what you tell it to do, nothing more, nothing less. So firstly, compute the results. So when you're computing the model, so run this DLM command and call something logical, and then make sure what you call it in the first step is what you apply the summary command. Step, so summary low 1.glm. Second step, 2.glm in the first step, summary low 2.glm in the second step. just to recap how the GLM command is working, so you've got in this case a generalized linear model, y-low related to region, normally equals binomial, so just to emphasize to R that you're wanting it to fit a probability regression model, not a classical linear regression model, and you can specify a probit model if you want to. And then, exactly as said before, these models can serve as a cross-check of each other in applications. So the thing to watch for here is you'd expect to find similar models giving you similar interpretations and numerically similar estimates on a practical data set. So calculating on the probability, somebody gives a low score from the logit model. So what we've done is run the commands on the previous slide, picked out these t-statistics, and remember when we look at these t-statistics, it's really the second row downwards that's the interesting bit, because the default is to fit a constant or intercept term, and that's not going to be very informative in its own right. So here what we have is, if you look at the p-values in the final column of each row, all these p-values are bigger than 0.05. Okay, so if we take this at face value, all you would need for the assessment for the module or an exam style question would be no evidence, p bigger than 0.05 for regional differences in the extent to which people award low scores on these surveys. Okay, and then the thing to emphasize here is this would be exactly what you'd need in the previous example, with the p-value being slightly bigger than 0.05 in terms of the assessment, but you might get more nuances in terms of the interpretation if it is borderline significant, p less than 0.01, compared to if it's definitely not significant, p bigger than 0.1. So this interpretation you've got on this slide is all you need for the assessment for the module, but on occasion you can have more nuanced interpretation of p-values required for dissertation projects if the p-value is less than 0.1 or bigger than 0.05. Similarly for the probit model then, so the R commands are on slide 3.10, and again what we've done is taken the R output and just extracted the t-statistics. Again, it's the second row downwards where the interesting action is, precisely because the natural default is to fit an intercept or constant term, which isn't usually very informative and interesting in its own right. So if we look at the p-values in the last column of each row, in each case we've got no evidence, p bigger than 0.05, that any of these terms is significant. So if we take this at face value, again the sort of thing that you might need to state for the assessment, no evidence, p bigger than 0.05 for regional differences in the extent to which people award low scores. So again, what you're seeing with the practical data set example here is that you get similar looking interpretations from similar models, here the logit model and the probit model. Okay, and then a relatively easy interpretation here, p bigger than 0.5, no evidence of a regional effect in this case. So we can be fairly confident that we are on the right lines here, because we've got the same conclusion out from firstly a logit model and then secondly a probit model. So alongside that I want to do this final check. So I said there, what is the probability that somebody will sit on the fence? So the idea is that we can calculate the probability that somebody gives a medium score in the survey, and there shouldn't be any detected regional effect because everything should be contained in the first two equations, calculating first the probability of getting a high score and then the probability of getting a low score. So classical binomial model is constructed for the special case of two categories. In this case we've actually got three categories: high scores, low scores and medium scores. So you need two regression equations to separately estimate the probability of obtaining a high score and then the probability of obtaining a low score. Though this is technically a redundant step, I think it's instructive to fit this third equation to estimate the probability that somebody will sit on the fence and award a medium score on this survey. The thing that's going on here is if you have n categories, you need n-1 probability calculation. So the classical case of two categories for these binomial models, two categories, so only one probability calculation needed. Now mathematically the technically correct analysis would be to use something called multinomial regression models, corresponding to multiple greater than 2 categories. I haven't discussed that here. I wanted to restrict to the simpler binomial case because that's still instructive.